So yes, the realization of fetal heart MRI has some special requirements, like for example having high spatial resolution due to the small fetal vessels and chambers, having high temporal resolution due to the fast fetal heart rate. It automatically sorry. Because the slides are automatically changing. I hope this works now. Sorry. Okay. So yes, high spatial resolution, high temporal resolution. We need to guarantee the coverage of the complex fetal cardiac anatomy by either having specific scan planning or by using 3D imaging. And we have to find a way to deal with the maternal and the fetal motion by having, for example, short scan times and by implementing motion correction algorithms. Many of these challenges have already been addressed for 2D acquisitions, and slice-to-volume methods have already enabled 3D reconstructions. But nevertheless, motion remains a limiting factor, especially for 3D acquisitions. That's where our goal and our approach was to create a platform for optimizing 3D fetal cardiac MRI, taking us from in silico simulations to real in utero data. To account for the flexibility in testing our whole framework, our framework was built up as an in silico simulation framework. The data for our digital phantom here was created out of high-resolution CT scans. CT scans which have been segmented and mapped with the respective MR relaxation properties. And with the proper sequence parameters and analytical signal equations, we could then convert those map regions into MR contrast. Additionally, 3D rigid movement has been added to our digital phantom. The range for the translation has been plus minus 10 millimeters in 3 dimensions, and for the rotation was plus minus 5 degrees. The simulated k-space acquisition was a 3D radial phyllotaxis trajectory and took around 6 minutes to get an isotropic resolution of 1.5 millimeter cube and a field of view of 288 millimeter cube. 50 datasets with variable motion have been created according to this manner. And for the proof of concept, one dataset with the matching scan parameters has been acquired in utero. To walk you now through the whole framework. After each shot of the 3D radial spiral phyllotaxis trajectory, an SI readout is acquired to then be used for the maternal respiratory signal extraction by filtering the principal components of those SI projections according to the free-running framework, like Matthias presented in the morning. Sorry. Unfortunately, this approach is not working for the signal extraction of the fetal cardiac signal due to factors like maternal fat, fetal bulk motion, and also fetal cardiac heart rate, like we heard in the morning. That's why we have to use the help of an external device, which is in our case an MR-compatible Doppler ultrasound gating device. After this, the acquisition gets temporarily bent into real-time frames with a resolution of around 15 seconds. Sorry for the switching of the slides. Those 15 seconds give us a good compromise of the undersampling artifact we're having and the temporal resolution of the fetal bulk motion. Afterwards, those real-time frames get first corrected for the maternal respiratory motion with a focused navigation algorithm called FNAV. This algorithm takes the previously extracted maternal respiratory signal and scales it into in 3 dimensions according to an image entropy metric. Oops, sorry. according to image entropy metric, and applies this scaled signal as a translational displacement to the respective real-time frames. To account then afterwards for the fetal bulk motion, we have implemented a 3D rigid registration. This registration takes in 3D region of interest as an input. So by default, not the whole field of view has been registered to, which basically accounts for the different movements of the different fetal body parts. So in our example for fetal heart MRI, we are choosing a region of interest around the upper body of the fetus. From all of the real-time frames, then the frame with the highest mutual information within this chosen region of interest is taken as a reference frame to which all the other frames are then registered to. To account for the cases where our registration is not working properly, thus where our fetal bulk motion is not estimated properly, we implemented also an outlier rejection algorithm. This algorithm analyzes the signal difference between the reference frame and the registration output to reject those frames where the motion has not been estimated properly. With all those motion estimates of the maternal respiratory motion and the fetal bulk motion, we are then able to correct the acquired k-space. And with the fetal cardiac signal, we are able to bin the k-space into 20 cardiac bins. And with the help of compressed sensing, we are able to reconstruct 4D images finally. Yes. To, in the end, also verify the function of our single motion correction steps, we implemented a blur quantification for the in silico data by comparing an ROI of the reconstructed data, here shown in green, with an ROI of the in silico ground truth, here shown in blue. The standard deviation of a Gaussian blur kernel has hereby been taken as a blur metric, and it has been varied to basically match the blur degree of the final reconstructed data. Looking now at the in silico results, we're seeing 3 axes of the real-time reconstructions, which are leading to strong blurring in the 3D static reconstructions due to the fetal motion. The 3D static reconstructions with motion correction and outlier rejection are showing that the motion can be estimated to a good quality and that the blur level can be significantly reduced. As a reference, the ground truth of the in silico phantom is shown on the right column. The in utero results are showing here the 3D static reconstructions of the uncorrected data on top and the motion corrected plus outlier rejected data on the bottom. The green arrows are hereby highlighting the fetal cardiac chambers, which are getting sharper, sharper after motion correction. Finally, to show the motion corrected 4D in utero data set, we're seeing the dynamics of the fetal cardiac chambers. And this is also highlighting again the advantage of our 3D acquisition with the possibility of a seamless transition between the different cardiac chamber views. So to summarize, a 4D fetal cardiac MRI framework has been created to optimize the acquisition and reconstruction. It has been tested first in silico, and the proof of concept has been shown in utero. Finally, motion-corrected 4D images of the fetal heart from a continuous 3D radial acquisition have been shown, and in general, a way and a manual of doing fetal heart MRI has been shown. Further investigation has to be taken to determine the degree of correctable motion in general, and to improve the acquisition, as well as other steps towards the reconstructed image, like, for example, coil selection or maybe as well implementing AI. Thank you for your attention.